Okay, today we're going to start talking about chemical equilibrium. What does it mean? How do we won't solve for them today, but taking a look at what implications does that mean for us in chemistry. So first, let's make sure we define what is equilibrium. So equilibrium is the state in which the rate of the forward reaction equals the rate of the reverse reaction. So it is a dynamic state where you still have products and reactants reacting to each other, and it's when the rate of those two forward and reverse reactions equal to each other. So an example would be, if A is going to B, but at the same time B is going to A, we'll say every 1 second 1A turns into 1B, but every 1 second 1B turns into 1A. Well, your net change is 0 because I'm losing one every second, but I'm also gaining one back every second. Okay? Right there, that is when the rates are equal to each other, So this is the state of equilibrium. Now, a byproduct of this is what we notice is the concentrations, because the rates are equal, the concentrations of the products and reactants stays the same. Okay, so since the rate is the same, you get no, with our example up here, we get no change in A. If you come back 20 seconds later, say you had 10 A's, and every 1 second you're losing one, but every 1 second you're gaining one. Well, if the reaction keeps going on, no matter when you come back, you're still going to have 10 A's. Okay, so the concentration of the products and reactants stay the same. That doesn't mean that the concentration of A is equal to the concentration of B. It just means that we have no change in A or no change in B. Okay? And if you were to look at this graphically, it might look like something like this. So let's say we have time here on the x-axis, and we have concentration here on the y-axis. I kind of squeeze that in. And let's say we have that reaction. We'll say we start with no B. I'll change some lines and colors here. So say B is that color, and let's go A with this color, okay? So say we start with some A, and what we see is the concentration starts to drop, and it starts to level out eventually. That's a terrible straight line. Let's say with B, if it's your product, say you have none initially. Sometimes you can start with products, though, and still reach equilibrium, and you increase, and that, okay? Well, this point right here, if this is a better drawn line, it would be nice. This point right here where we see the plateauing of our concentrations, okay? That's better. We see that plateau or our concentrations aren't changing anymore. At this point right here, now we reach equilibrium. All right? Before here, where you're still having a change in concentrations, that means that rate hasn't set, the rate of products to reactants hasn't equaled out yet. But as soon as you get a constant concentrations, okay, that's when we have equaled out, and now we're at equilibrium. Right? So the big thing with this is, well, how do we solve for this? Okay, with this, how do we know what the rates are and stuff like that? Well, what we're going to look at is we're going to look at equilibrium constants. Okay, and they can be a lot of things. KEQ, KC, KP, KA, KB, KSP. All these Ks are equilibrium constants. Okay? And the biggest thing about equilibrium constants, and this is critical, you've got to know this, an equilibrium constant is a ratio. That's all it is. We've got to know this, okay? We just want to look at it as a ratio. And what it is, it's a ratio of the concentration of the products divided by the concentration of the reactants. Okay? That's all it is, and that is critical. So when we're looking at our K values, there's nothing magical about them. They're just, hey, how much products do I have versus how much reactants do I have? And this is at equilibrium. And that's critical. This is only at equilibrium. Right? It's not at any point in the reaction. So, if you go back up here and look at this, you can't calculate a K here or a K here. You can only calculate a K here past the point of equilibrium. Okay? And they're all called equilibrium constants. So K constants or equilibrium constants are constant at set temperatures. Okay? So they are constants at set temperatures. Or in other words, the only thing that can change a K change the value for K is changing the temperature. Okay? For a given reaction, right? So the only thing that can change K is changing the temperature. Right? Everything else is going to keep K is still going to be a constant at a given temperature. All right, so how do we write them? Let's take an example. Let's say we have this general formula. AA plus B moles of B goes to C moles of C plus D moles of D. Right? So your K for this, I'm going to just use a KC for concentration. Now, if you remember, brackets tell me concentration. So concentration of A raised to the coefficient, A power, times concentration. That is wrong. That's reactants. Let me try that again. The concentration of C raised to the C power times the concentration of chemical D raised to the D power, the coefficient, divided by the concentration of A raised to the A times the concentration of B raised to the B. So that's how we write. This is your general formula for equilibrium for for KCs, KS, and all that stuff. So an example with a equation, a really well-known equation, the Haber process. So we have N2 gas plus 3 moles of H2 gas goes to 2 moles of NH3 gas. And if I wanted to write this K for this, just the equilibrium expression, Kc is equal to the concentration of NH3 squared, coefficient, divided by the concentration of N2 times the concentration of H2 cubed. So there's all the, now, if it's a Kc or Keq, you must use brackets. So if we remember back, brackets equals concentration. And that's what we're measuring at equilibrium, right? We're in this, the concentrations of these things being constant or equal to each other. So say we had some values for equilibrium, for this, say, and I'm just making these numbers up, so these probably aren't, say at 200 degrees Celsius, it is found the following equilibrium concentrations. So let's say concentration of N2 is equal to 1 molar, concentration of H2 is equal to 2 molar, concentration of NH3 is equal to, let's say, 0.5 molar. Okay, so let's say those concentrations are found. Well, since they're at equilibrium, what we can do is we can just plug those in, 2K here, and solve. So we have 0.5 squared, right? 0.5 squared divided by 1 times 2 cubed. Okay, and when we plug that in, again, these are made up values, so if you look up in a chart and say, hey, this isn't the KC, you're right. So what we find is the value for KC is 0.031. Okay, no units. This is a unitless number because it's just a ratio. Okay, and so anytime you have equilibrium concentrations, you can plug those into your K expression and solve for the value for K. All right? So let's go back. We said that K constants are a ratio, and let's take a look at what that means down here now that we've done a problem. Okay, well, let's say at 200 degrees Celsius, the ratio for that equation comes out to this. Well, then we can talk about what reaction is favorable. Okay, well, so my concentration is this, or it's less than 1. My K value is less than 1. And therefore, what we know is the forward reaction, or the products, really aren't favored, right? Most of my chemicals are still what? The majority of my chemicals are still reactants. Okay, so if K is less than 1, it means the reverse reaction is favored. So the opposite would be true. Say K was greater than 1. Okay, say you switch this to, instead of 0.5, say it was 5. And then you'd get that squared divided by 2 to the third. That would have given us a value of, if it was 5, of 3.125. Well, now what do we know? Well, now my products, or my numerator, is larger, so the forward reaction is favored. So K's tell us a lot of things. The value of K is going to tell us, hey, what reaction is actually favored or thermodynamically favorable? In this case, the reverse reaction would be thermodynamically favorable. In this case, the forward reaction would be thermodynamically favorable. Okay, so what we'll start do then too is now we can start relating to K to delta G and Gibbs free energy and stuff. But so here's a little quick intro with equilibrium. What is equilibrium? It's the state in which the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, and a byproduct of that is the concentrations of the products and reactants do not change. So therefore, we can set up this ratio of concentrations at equilibrium. That is a constant, a K constant. So our equilibrium expressions or equilibrium constants. All right. That's all we got for today.